So we are in a very exciting period for the semiconductor industry. Changes in architecture, changes in the growth of the business, which Ajit pointed out to you. We just grew in 2017 22%, followed by 15%. Consider, in the previous 6 years, the average was less than 3%. In the previous 2 years, it was less than 0.5%. So unexpected for the industry, big growth. But of course, as was also noted, memory was the primary semiconductor growth driver. In fact, the memory market grew 60% in 2017 and continued its strong growth in 2018. Well, now, as a result of this, the memory revenue as a percent of total semiconductor revenue has now grown to 40%, or nearly 40% of total semiconductor revenue. And over history, memory has been 27% of semiconductor revenue. So one has to ask, is this temporary? Is this an indication of something new? And for that, we can look at data. So this is the average unit price, and I would point out that over 70% of the growth of memory in 2017 and 2018 was caused by price, not volume. So you take a look here at the MOS logic is in yellow, and we have, basically it's on the long-term price trend. And so is analog, which is shown in green. What is not is memory. Notice, the average selling price of memory soared in 2017 and 2018, just as it did during periods of shortage, like when Windows 95 was introduced in 1995, and a shortage occurred, when the dot-com boom drove another shortage. So this is a period which, if we look at history, is temporary. Well, it turns out that unit volume in the semiconductor industry is very predictable. It follows a very consistent curve that can be modeled, and as you can see, the unit volume of memory has been increasing, but is right now below the long-term trend. So we had a period that after the dot-com boom where wafer fabs were not built for a while and volumes went lower. Then in 2010, things took off and volumes went higher. And so now we are in a period where we are not shipping as many units of memory as history would say we should. Now, if you look at these kinds of curves, one thing you find if you've been in the industry as long as I have, which most of you have not, you find that when you get below a curve or above, they tend to be symmetric. So the number of units that we were short in this period is roughly offset about 19 billion units of memory that we had to catch up with. So one then asks the question, what about now? We are actually behind in unit volume. We need another 6 billion units over the next 3 years or so to catch up with the long-term curve, which means we need to accelerate, not slow down, our unit shipments in memory. Well, units are a convenient thing to look at, but what's more meaningful is to look at transistors, because we can plot everything in the semiconductor industry in terms of transistors. And what do we find? We find that for logic, we are right on the long-term trend, right about where we should be, but for memory, clearly, we are running behind in terms of the number of transistors. So one wonders, what's going to happen over the next few years? Are we going to catch up? And I think there's a good chance we will, but the question is, at what price? So we have to look at the price per transistor, and for that, we have lots of semiconductor history. We have what's called a learning curve. If you are not familiar with learning curves, I'll introduce you. So in a learning curve, it's a log plot. They've been used throughout the history of our industry and for 100 years before. You plot the log of the cost per unit produced, and you plot the log of the cumulative number of units produced through history, and you will get a straight line as long as you have a free market. And every time you double the cumulative unit volume, you will decrease the cost per unit or the revenue per unit by a fixed percent. So here's the data since 1954 for the total semiconductor industry. A near perfect straight line, as it must be, because as Moore's law is temporary and goes away, the learning curve never goes away. It will be true forever. Right now, at this point, we are reducing the cost per transistor about 32% per year. But if you look more deeply at the learning curve, it's made up of many diverse components. And so let's say we break out the flash memory and DRAM from the rest of the semiconductor learning curve, and we find that the number of transistors that we are producing in memory far exceeds the cumulative number that we're producing in non-memory. And not only that, the price per transistor for memory transistors is decreasing at 35% per year, while the price per transistor of logic transistors, or at least the rest of semiconductor, is decreasing at only 23% per year. And you'll notice something else. Over here, we are above the learning curve. We are at a price that is higher than the long-term average can sustain and still obey the learning curve. Now, having run memory businesses for a phase of my life, I can tell you we always plotted the learning curves, and whenever we saw this, we knew sooner or later this was going to come back to the learning curve, and not only come back, but it was going to go below the learning curve to offset the period of joy and fun we had when it was above the learning curve. So, let's suppose that we, in fact, hypothesize the increased number of transistors in the next couple years, and that will lead to increased units of memory and correct some of the oversupply. Prices come down. Then what does that say about pricing? Well, we get the units from the trend line assumption. We get the transistors from the transistor trend line assumption. So therefore, we know revenue per transistor from the learning curve, and we know transistors per unit by calculation. So we know revenue per unit or average selling price. And that, in fact, is what's shown here. This is the actual data, including an estimate for fourth quarter of 18. What this calculation says, if you assume that those assumptions I gave are correct, is we've got at least 2 more quarters of fairly rapid decline in overall memory price, then a slower decline through 2019, but surprising to me, stabilization and even modestly increasing prices in 2020. Now I'll remind you, this is total memory. DRAMs experience a much bigger price rise than flash memory, so it's quite possible that you could have continuing decline of DRAM, but moderated by the increased bits of flash or transistors in flash that we produce. But what you really care about, although price is important, is revenue. What's the revenue going to be as we look ahead? And if you take those units and you multiply them by the average price, then for total memory, you would get, you would get a decline in memory revenue of about 10% in 2019, and then stable and a little bounce back in 2020. This I found quite surprising because it's not typical. Usually when we have a boom, the bust is much deeper. We'll see what the actual numbers come out to, but this is my piece of the let's be quantitative and see what the market says. Now, is there enough capacity to handle those additional 6 billion units? And can we really increase the unit shipments? And I would say without a question. In 2017, if you look at flash capital investment and DRAM capital investment, it doubled compared to the average capital investment in prior years and increased another 50% in 2018. So I'd say we probably have the capacity between Korea and China and a few other places to in fact meet the increased memory demand. Well, will the market be able to use it all? After all, we could have a big excess. So that's where I look at the mega trend going on in memory and how it relates to artificial intelligence. Consider, if you just take discrete devices and count the memory transistors, forget about memory transistors that are embedded in microprocessors, just discrete devices. Back in 1990, 45% of all transistors were memory transistors. That number has been increasing steadily, so today, almost all of what we produce is memory transistors. This only goes through 2015. We are probably about 99.9% memory transistors, largely thanks to NAND flash, but at any rate, it's all memory. And it is inevitable that that accelerated growth of memory transistors will continue because NAND flash is growing vertically, because we've been able to increase the memory bit capacity simply by originally adding bits per cell, but in recent years by adding layers, and it looks like we're still in the early stages of that. We can go much further. Well, think about the way computers work. We have been stuck with von Neumann architectures for a long time, with instruction and data streams being the bottleneck, and now we're looking for more performance. And in fact, von Neumann architectures really provide the bottleneck. And in fact, if we look at human processes like facial recognition, pattern recognition, all these things, your brain is able to do in a few hundred cycles what a von Neumann computer requires millions of cycles to do. The architecture has to change. And so we are entering a new wave of domain-specific architectures. And if you talk to people, and this is not new information to anyone, but I just chose the speech that John Hennessy, the former CEO of Stanford University, gave at the Electronics Resurgence Initiative that DARPA sponsored in May. And you look at his comments, basically his thesis was, we know Moore's law is dead or is dying, and yet we have been using much of the performance that we have gained in hardware to make the life of the programmer easier. We've had scripting languages that are run interpretively, they're dynamically typed, we encourage reuse of software. Everything makes the programming easy, but what do we do about lowering power dissipation and improving performance? And his and other views in the industry are we have to develop domain-specific architectures that do just a few tasks, but they do them extremely well, and we end up with domain-specific languages as well as architectures. So let's look at what's going on in the industry. This is venture-funded, fabless semiconductor companies. There was a big peak of $2.5 billion of investment back in the year 2000, and it's been declining ever since, stepping down until 2017. All of a sudden, we jumped from roughly $350, $400 million a year to, in a single year, $1.4 billion, and more recently, in 2018, 3.1 billion. Now you may say, well, that's all Chinese investment. It's not all Chinese investment, although it is very heavily Chinese, more than half, but it's spread in a variety of areas. Now, if you look at the early round funding, rounds 1, 2, and 3, I find it very remarkable at the number of first round startups. Notice the light blue is first round. Very speculative. That's true entrepreneurial kind of investment, and lots of money going into first round investments in fabless semiconductor companies, something that had gone out of vogue with all the new students who wanted to work in social networking, with all the venture capitalists who wanted to fund other kinds of companies. Now, they're funding fabless semiconductor startups. Well, looking over the last 6 years, I've tallied up how much money has been put into different kinds of processors. And without a question, by far, the dominant investment is artificial intelligence and machine learning. Roughly $1.8 billion of venture-funded startups going into AI. Well, artificial intelligence is really not a new trend. Let's go back to 1986, 32 years ago. This is the cover of High Technology magazine talking about artificial intelligence. Heavyweights get into the act. Does anyone recognize me? That's George Hallmeyer, who was the head of DARPA, and that's when I was at TI, and we thought we were into a gold mine. But in fact, it really didn't take off back then. First of all, we really had a lack of big data and a way to collect the data. We had very limited computing power. We needed more advanced algorithms. But the biggest thing was we had a lack of killer applications where people could make money. Well, those limitations have largely gone away. And so now, if you look at 2018 alone, there were 24 fabless semiconductor startups funded. And this is all rounds of funding. But if you look at what they were doing, it covers the complete the range of things that you just heard about in voice recognition, pattern recognition, but a variety of others. All sorts of network processors and neural decision processors and AI engines for autonomous drive and so on. And while it's true, sense time, facial recognition from China, 1.2 billion, a big piece of the total. Most of these were much smaller, and most of them are developing chips for far less money than we used to think was required to do a custom big digital design. So let's look at what makes up all of those. And I've categorized them into the various types of AI processors. And by far, the largest number are in what I would call pattern recognition, which is what we've been talking about for the last hour. Certainly, facial recognition is a big category, 39 of them. But they're also everything a human does in pattern recognition. Recognizing things you see, smells, sounds, other voices, all these things are human-like AI, which can benefit from special purpose architectures and languages to do them more efficiently. The second largest category, second largest category is, is the data center. Oh, excuse me, yes. This is an example. This is the one done at KAIST. You saw the one done at Samsung. Lots and lots of facial recognition processors that are running very low energy and very high accuracy, but all sorts of other visual pattern recognition processors. The second largest category is data center or cloud-based accelerators of one sort or another. And these are heavily influenced by designs done at Google and Facebook and Amazon, Alibaba, Tencent, all these companies who are trying to execute their artificial intelligence algorithms faster than their competition and doing special purpose processors. And there's a whole family of companies, NVIDIA with its AI platform out in the market. We have Xilinx doing preprocessors for the servers and Intel acquiring Altera for the same reason. Dozens of companies, Graphcore and others, that are doing all sorts of accelerators for AI processing, principally in the cloud. And then we have edge computing. Now, a lot of these could be considered edge computing as well. You just heard this morning that you cannot guarantee connectivity of a car to the cloud, so we have to do more and more of the processing at the edge. And so many of these are dedicated to that kind of edge processing for pattern recognition and other functions. And there are lots and lots of companies that monitor your eyes while you're driving to see what you're doing and to track your actions. AI chips that are designed to handle failures and fault injection and respond correctly. There's an Israeli startup that's introducing a deep learning chip that's gotten publicity, totally automotive grade, and so on. Dozens of these in the works, and there will be some winners and, of course, some losers. Well, all this innovation occurring, all these new startups, how long is silicon going to be the vehicle, and when do we have to go to a new switch? You have lots of people experimenting and talking about what comes after the silicon transistor. So I'm going to do another speculative forecast, and for that, I turn to a man named Benjamin Gompertz, who in 1825 proposed a model for time series that would model the way things evolved with time. It was used for the growth of tumors, used for population growth, used for a variety of things that has stood the test of time. You would think of it as an S-curve. That is, things start out slowly, and then they reach their critical mass, they take off, and then the last few percent takes a long, long time. Well, it turns out mathematically that's a double exponential. There are three coefficients, A, B, and C. T is for time, and this is an exponential, this is an exponential, and the change in the coefficients determines the shape of the S-curve. Well, so let's try it out. Take the number of cell phone subscribers, this is the actual number as the industry has evolved, and then go back to 1997 and assume you only had a very small amount of data, 4 or 5 years, and you took that data and you solved for the Gompertz coefficients, A, B, and C, and then predicted what will the uptake of cell phone subscribers look like. Well, the answer would have been this. So your forecast would have said this green line, this yellow line, and the actual is the green line. Now I have to conclude the reason it's not perfect is that back here we assumed that humans had cell phone subscriptions. Now there are lots of machines and non-humans that have cell phone subscriptions, so the model doesn't work well if you change what you're measuring. So let's take one where we're not changing it. Take the notebook computers. So here's what's happened with notebook computers, still a growing market. Go back to 2001. Take the actual data in 2001 and solve for the Gompertz coefficients, and then plug it in the equation, and what do you get? You get a very accurate prediction of the future. In fact, if you were a supplier of notebooks back in 2001 or a supplier to notebook manufacturers, this would have been quite helpful to know exactly how the market was going to grow. So, there are lots of interesting markets. I won't go into all of them, but I do want to point out one, and that's the data center. This is one of the dynamite semiconductor markets because you can see we are still in an upward curvature. That means the growth rate of shipments of semiconductors to, of servers is actually increasing. The rate is increasing, so the number's increasing rapidly. Right now, it's over 4%, actually approaching 5% of total semiconductor revenue, and it's going to grow faster every year with no end in sight. Really great market. No surprise that companies like Avago and others have focused very heavily on it, as well as Intel. Well, now what you really care about. How long do we have jobs designing with silicon transistors? I've taken this one on as well. And so if you looked at the curve here, you'd say, wow, we've hardly shipped any silicon transistors at all. But if you look closely, we're actually in an accelerating phase of the life of the silicon transistor. So one wonders, how much longer does it go on? Here is today, and here is when the second derivative goes to zero. That is, the growth rate stops increasing and starts decreasing. And there you have it in 2038. The growth rate of silicon transistors shipped will stop accelerating, and the growth rate will slow until in 2050 or thereabouts, 2055, the market starts to saturate. I personally am not worried about this for my career, and for most of you as well, but it is consoling to know that that's what Gompert says about our business. Okay, so to summarize, we've had a sudden acceleration of growth of semiconductor revenue starting in 2017 and continuing into 2018. Memory unit volume is actually below the long-term trend, but the unit prices are above the long-term learning curve. So we can expect decreasing memory prices on average, that's the average of all memory, in 2019, and that'll be offset some by the fact that the unit volume growth rate should increase. We have continued non-memory market strength, especially in logic and in analog, because of the introduction of domain-specific processors, because of the acceleration in new startup activity, as well as the entry of new companies into designing integrated circuits, like the system companies, automotive suppliers, Google, Facebook, the whole crowd. And finally, an astronomically large investment by the Chinese in overall semiconductor development, both process and design. And finally, domain-specific architectures and memory unit growth will enable the next wave of semiconductor industry growth to achieve the lower power we need, the higher performance, and the lower cost. And by the way, there's been a clear reduction in the time and cost of designing a custom semiconductor. So we've opened the door to a whole group of new people to innovate in this technology and grow our industry. 감사합니다.
Thank you for the talk. So this talk is open for questions or comments.
Thank you for the inspiring talk. My name is Sam Hong from Myeongjin University. One of your talk, in your talk, you point out domain-specific language and architecture. I think I understand domain-specific language, but I'm not still clear what's the domain-specific architecture stands for in your term. Could you explain on that?
Yes, so you saw some examples in the first talk of the particular types of computation that are required and where the bottlenecks are in terms of performance. So as we develop processors with extensive parallelism, we're faced with the issue of how do we implement that so that we can vectorize the application. That is, so we can throw many processors at it. And if we narrow the domain and say the data will be of one type, for example, graphics, the problem is much easier, but you still would like to have primitives that match your instruction set in such a way that you can very quickly execute them and process that data to, for example, compare images, compare voice snips, compare genetic data. And that's what I believe most people mean by those domain-specific architectures.
Okay, another question or comments? Sam, one question. So outlook for semiconductor memory has been changed. Now, how can you summarize the one simple phrase? Could you tell me
The simple phrase that describes how
Yeah.
memory is changing?
Yeah, how? Can you summarize?
Simple. First of all, memory as a percentage of our total semiconductor production continues to increase, and we find new ways of using memory to do what used to be logic functions, and yet we can use memory in both the compute process and to solve problems if the memory is very inexpensive and the architectures can be adjusted so that they can take maximum advantage of that growing availability of memory.
Thank you. It's a very good
Thank you.
sentence.